True. Anyway, hello everyone. Welcome. I'm not even gonna pretend, and I'm just gonna leave it on the not presenting screen, and we're just gonna move through them click by click. But I'll be talking about diffusion planning, general imitation learning, with the context of this robot that I've been working on. That it's just a very low cost platform for tactile task doing, and I'll get to it in a bit. I have an agenda. I'll talk about what imitation learning talks about. We'll formally define some things that matter. Then we'll talk about the robot, and then I'll dive deeper into the mathematics and properties of diffusion policy.
So does diffusion planning have anything to do with, like, I know diffusion in the sense of like vision models? Is it the same?
Region models.
No, sorry,
Vision model. Yes. So it is similar, and like I put at the beginning, we are planning with an image generator, which is wild.
Okay.
But the core idea of it is that we're going to be generating a trajectory instead of generating an image. And I'll get to that more when I get into diffusion planning.
Okay.
I want to cover the idea of imitation learning a bit more first, just for people who might not know. So for those who aren't aware, imitation learning is we have a demonstration of a task being done, and then we're going to learn how to do the thing. We're going to learn how to do the task. There's two flavors of it. There's behavior cloning, which is monkey see, monkey do. That's basically what diffusion planning will end up being. There's a few other flavors of it that I'm not really going to go over, but you know, direct. I have an action. I have a set of states and then actions, and then I'm going to learn in a neural network that will map states to actions. That's just direct behavior cloning.
Okay.
Then there's other ideas like Dagger and Gale, which you can look up on your own. But they follow the same idea of I have data and I'm just going to directly create more data, basically. Then there's the more complicated and, to me, more interesting inverse reinforcement learning, which tries to figure out the why behind the demonstration. An example for this is like it tries to learn a value function or a reward function for the demonstrations that are given to it, that it can then morph and apply to the problem it's going to do, and then apply another more simple algorithm like a heuristic search or whatnot in order to do the rest. So formally, in this, what we are specifically learning is we have a data set of trajectories. This is going to be given some tasks. I have, as an example of a task, I have some cats that I printed, and then some colored dots. I don't know how visible.
I think
It's kind of visible. And then we can shuffle up the cats, put them on different colored dots, and then a task could be reorganize these cats onto the correct dots. And in doing so, the robot arm will move through different positions and grasp the cats and move the cats around, and etc. And all of that can be represented in a sequence of states and actions and states and actions and states and actions. For example, move the arm forward. Yeah. See if I can do it. Pick up the black cat. Or fail to pick up the black cat. It needs a slight amount of debugging. Good robot. Um, gosh, it needs a bit of work. From this data set, we want to make a model. That model can be the classical model of given an action, or given a state, give me an action. This is commonly written as pi or a policy. Or in the case of what we're doing, is just a straight probability of a trajectory happening. So a straight probabilistic model of a trajectory, which you can just sample directly. Things that we generally want, optimality would be nice. The ability to have multiple goals, that is to say, shuffle around the cat's a bit different. We also want to not have to worry about how long the plan has to be. And I'll show how that works. One of the biggest challenges with this kind of paradigm of solving this problem is multimodality, which is the idea that there are multiple different ways of solving a problem. So the data will therefore have multiple different modes within it. There will be a mode in which we move this one out of the way and move this one here, then move this one here and move this one here. But there are other modes in which we solve the problem in a slightly different way. Moving a different cat into a different spot.
Okay.
And if we're just going to try and learn a direct state to action, it's essentially going to try and average all of these different modes together into one way of solving the problem that doesn't necessarily exist. So unfortunately, the robot is misbehaving on me at the moment. But this particular robot didn't actually cost me anything to make because I had all the parts. But I looked it up and you can get all of the servos for like $40 on Amazon. The wires at the makerspace are free. A knockoff Arduino is like $10. And then in PCA 9685, $10 maybe. This is a very cheap robot. And part of the other interesting thing about it is I found the design on the internet. Here's my attribution for the robot. All of the files were out there, and I've edited them a bit in order to make it work to my personal needs. But the point behind it is that anyone can make this robot for $60. Anybody can run these experiments. Anybody can, collect data and train a model pretty easily. It has a very simple state space in that we have just some angles, 4 angles, a base, what I'm calling the shoulder, the elbow, the wrist, and then a Boolean for just the hand, which is just open or closed. The hand is adorable the way it's made. It's just a rubber band that holds it closed, and then the servo opens it. That's a very inspired design. And for transition dynamics, the action is just the next state you want it to be in, as depicted by the little controller. So if I give it a next state, it will move to that state. I'm puppeteering it slowly because it's decided to break itself today. So given a very simple robot, we can even ignore the actions in a trajectory and just say we have state, 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 state. But I'll keep it general and say we have state action for other kinds of robots. You might have a car, where the state action dynamics aren't exactly perfect. The other thing to note with state action dynamics is there's stochasticity, and of course, having a half-broken robot kind of enforces this stochasticity on the world. Jumping directly into the deep end, this is going to become a bit more of a conversation with Himali about this. But in diffusion planning, the core paradigm of it all is to turn noise into data by turning data into noise. We start with a data set of clean data, and this forms a distribution, essentially, of trajectories. In this, we have a whole bunch of demonstrations of completing different tasks. And this distribution it'll have a bunch of different, it'll have a whole bunch of different elements within it, a lot of different modes, like we talked about before. The thing about it is the thing we're going to do with it is we're going to iteratively add a bit of noise as determined by this scheduling variable alpha in the equation, which I'll go over the equation and what all that means in a bit. But we're going to iteratively add more and more noise to it, and we're going to basically collect data on how the noise affects everything. And then we're going to then sample a random point in completely random noise and basically reverse that process with all of the data we collected on how noise and the data the clean data that we have interact. To this, we basically just put it into a Gaussian. We have our transition data, tau. I should note that there are two different time scales in this, which is interesting. In a trajectory, we have the time from the start of the trajectory to the end of the trajectory, generally called the horizon. And then in diffusion, we have time from clean data at t0 or tau 0 to completely noisy data at the diffusion horizon. I've decided to call it just because it makes more sense to me that way. So the Q function here, the forward diffusion, and noise in it will increase the diffusion time. So we're going to have the probability of tau I given tau I minus 1. So if we start at 0, the probability of the noise that we have, or n noise in trajectory given all of the trajectories that we had before. And this is just a Gaussian where we're going to add a bit of noise based off of our scheduling variable, which is effectively like, one could think of an example of this just being completely linear as 1 minus I over the diffusion horizon, or like we're going to slowly decrease from its 100% data to 0% data, 100% noise. So at the beginning, our variance, this 1 minus alpha I times the identity matrix, this is our covariance, is going to be very small, and then it's going to increase in size. And then this is basically just math cheating, but we're kind of shrinking our data a bit when we're multiplying it by the square root of alpha I. So It gets complicated when we start trying to reverse it. We introduce this theta parameter here, which is just the parameters for the neural network.
I have a question.
Yes.
So for the forward diffusion process, you just have alpha, and do you vary it or do you like decide it? You just
Oh, so alpha is predefined. It's the scheduling parameter. So it just varies from 1 to 0. It can be linear from 1 to 0, and
So are you saying it varies as noise is being added, more and more noise, or
it defines how much noise is being added.
okay.
So it
And then
defines
it stays constant once it's predefined
for each diffusion step. Yeah.
for each diffusion step.
Right. Yeah. So you can think of it as this is the parameter that defines how much noise is happening at this diffusion step.
Okay. And so this adding of noise is not something that the neural network learns. Like that's not known.
No. That is predefined. So the adding of noise, because we've defined our the way that the alpha parameter varies beforehand, the adding of noise is the same every single time we do it. And generally this is how it's done. Where we just have a predefined forward diffusion process. And a lot of the time it's kind of ignored in the literature. So I wanted to give it a bit of a highlight and say this is what's actually happening.
So can I think of it like as some hyperparameter?
It is exactly a hyperparameter. Sorry, it's a hyperparameter function where it maps I to 0 to 1.
Okay.
In this case, I completely ignored. You'll see in the literature there's a beta and an alpha, where alpha is 1 minus beta. Thanks, guys. So I've ignored beta completely and replaced it in every instance with 1 minus alpha, so that it's a little bit less confusing. The original paper for this, real great, guys. Totally not difficult. Cool.
Yeah.
In the reverse process, you'll notice there's a lot of just theta in there that's defining what is happening. We have defined our the key thing is our mean is completely learned effectively. We'll get into how in a bit. One thing of note is that our variance is known from the start because it's defined by our Q. It's exactly 1 minus alpha times I. Well, it really isn't because we're going backwards. So it is the same variance. And you can also note that we're moving backwards. We're giving the probability of Ti minus 1 given Ti. And reminder that as I increases, we are moving towards noise. As I decreases, we're moving towards data. So given this sort of conditional version of it that gives us our iteration, we can do a fairly normal sort of Bayesian step of TH is complete noise. Notice there's no parameter there because it's Gaussian. And then TH minus 1 given TH minus 2 given TH minus 1. A funny note is that along the diffusion time, the process is actually kind of Markovian, and that it doesn't depend on any previous diffusion steps. But we'll get into what happens along actual trajectory time. It is not Markovian anymore, which is fun. And then you can do general log likelihood stuff. I forget what it's actually called. I didn't note it. Learning. You can just learn. It's very easy. Like this is regular for the learning literature. I'm not going to go over it just because it's usual. This doesn't actually tell you what's happening at all. This tells you the math behind what's happening, and it tells you the theoretical basis from which you can derive the actual mechanics of what's happening. So I want to talk a bit about more of the details of making this happen. And the key note is that they reparameterize the Gaussian to using just the regular like trick of the mean plus the variance times some noise that you can sample from a regular Gaussian from zero with 0 and a variance of 1. This trick means that we can have our neural network not learn anything related to the actual state space, but instead learn a 0 to 1 Gaussian error. That makes it quite easy, a lot easier. The other thing of note is that the mean depends not on or we're defining the mean to be some permutation of the current state at tau t, and the predicted error. So we're just saying that we're effectively saying we're at the mean, kind of, but we're kind of just pushing the mean towards pushing the mean with the error given the scheduling function that we have and some predictions on the cumulative effect of the scheduling that we have. I'm hand waving this away, but this is actually a pretty neat trick. But it means that we don't need to learn the mean. We can guess it. All we have to learn is the error at our current noisy trajectory. And theoretically, one could say, oh, we know the error, and then remove all of the error from our noisy trajectory and then be done. Which would be lovely if it worked. But instead, we're going to make use of our scheduling algorithm and actually step the error. And so the neural network actually predicts the total error at diffusion time t. And then we're going to temper it given the predicted variance. And we're going to do a sample as well in order to find our next predicted trajectory. We just straight sample from the usual Gaussian and add that to our known variance, which is 1 minus alpha t, and well, it's square root of 1 minus alpha t, and our guess at what our mean is. And that's going to actually be our update. The neural network itself, it's a UNet. You can learn what that is. There's probably a lot of people out there who knows what that means better than me. But the more interesting thing about it is that it is fully convolutional. And that kind of leads into some of the fun properties of it. So what does it being fully convolutional really mean? Is that we're only looking at the local region in time, in trajectory time, in order to predict the next state in diffusion time. So a better way, I don't know if I can really, I can point with my mouse. So to say this better, if I wanted to predict the actual state action pair, the things that I'd be looking at in order to predict this, what I'd be putting in is just the state action pair from the previous layer of noise. So we have a bit more noise, but the only state action pairs that I care about are the ones that are right next to it. So t-1, t, and t+1 in trajectory space. And this is what's going to be fed into our neural network and trained in order to learn the actual error that's happening. This means that all I have to do is train that little segment of a neural network and then apply it all the way down my trajectory, and I don't care how long it is. Which is great, because now I've got variable length plans. And it also means that I can do tricks like the disappearing horizon planning, etc. Another note on this is that what we get out of it in the end, because we're sampling from a Gaussian each step, what we get out of it at the end is a distribution. We have a data distribution. So in order to change the properties of the data that we want out of it, all we have to do is multiply by another distribution and we'll get a new distribution. So there's tons of math that has been doing this. And it's actually quite easy. So if we want optimality, all we need to do is train something that will predict the reward at each time step. Or not even predict the reward of a trajectory. And then take the gradient of that and then add that to our mean. And since we're adding that gradient to our mean, each diffusion step becomes its own little gradient descent step as it's pushed closer and closer to an optimal trajectory, based off of our prediction of the reward. And if we want to condition by a goal, there's this famous mathematician Dirac who came up with a function that he named the Dirac delta, which just allows you to say that the distribution will have this property. So basically it's 1 for when the goal and start are what we want it to be, and it's 0 for the goal and start are not what we want it to be. So all we have to do is multiply our distribution by this delta, and at each step there's a stopgap that'll say, okay, what's the probability that my goal is slightly different? Oh, it's 0. What's the probability that my goal is the same? It's 1. So at each step, it'll see that the goal and the state will stay exactly the same, and it'll find the states in between that work with that, which is neat. Yeah. So basically, that's it. That's diffusion planning. This is my robot. There's nobody here to play with it, which is okay. It's late in the semester. I did want to brainstorm shortly, like some tasks that I could have kids do, but I have my cat sorting task. I have an idea for, like, maybe you could draw something by having it grasp a pen, which it can kind of do.
Can I try?
Yeah, you can absolutely try. Go for it. I can operate the jaws. It's a little finicky just because things are not perfect. Oh, there you go. Yeah. because this was built by me, it's not perfect because I'm a human. If this was built, oh no, there you go. So there's a lot of noise in the different lines. One of the things is your fingers are actually touching some of the contact. So if you just grasp it like this,
Okay.
then it'll work a little nicer.
That's really cool.
Yeah,
Wait, so I have questions.
absolutely.
Um,
Yeah, it's trying. Yeah, absolutely. Questions?
I don't completely understand,
Absolutely.
but but basically, am I right to say that the neural network, instead of learning the mean, is learning the error?
Yeah. It's predicting how far off we are
Right.
on just a linear scale. Just neat.
Okay. So
I mean, I guess it's not really a linear scale. It's dependent on each of the different dimensions of the robot, I should say.
okay.
Yeah, sorry, my bad.
No, that's fine. And then if you go to the next slide,
This one?
yeah. So so it doesn't matter what your trajectory horizon is because of the fact that it's all convolutional layers.
Mhm.
Um, can you explain that again?
Okay.
Just the fact that you need that, yeah. The fact that is it because you just need to look at the states and actions around it? That's what
Yeah.
makes it
Exactly. So
like
when
Yeah.
we're training this particular thing, it all of the math is written with just the trajectory, which thanks guys. But what's actually happening is there's a convolutional layer that is just doing the same kind of averaging of each point into each other. And then we have a direct network. It's not a fully, is it a fully convolutional? Is it, no, it's not fully connected. Right. Sorry, I'm trying to remember how things work and not remembering perfectly. So
Okay, so if you go to the next slide,
I can't remember exactly how the neural network worked. I had it written down on a piece of note paper.
so it's like what I'm confused about is so what's the superscript?
So the superscript is in diffusion time. The subscript is in trajectory time.
And so on the previous slide, when it's an I, all of that is trajectory time. I mean I minus one, I minus.
Yes.
Okay.
Well, so when it's superscript, all of this
Oh,
is in diffusion time.
oh,
right?
this is in diffusion.
So
Oh, okay.
the sigma sub t is because it has to be squared, and I ran out of space. So that's my bad.
No, that makes sense.
Yep.
Okay,
So
I see.
it just does a convolution over these points here and averaging, if you will, over those 3 points, and then learns the error of that average from what it expects.
So superscript 0 is a completely like no noise.
Yeah,
Okay.
it's what we want.
Okay.
It's good data.
Okay.
Um,
Okay, that makes sense.
like what we're predicting here is the probability of any given t0.
Okay, so
a little hard.
No. So, I don't know if this is stupid, but
No, there's no stupid question.
so what was the data for this?
So the data for this, we have a state space, which is 4 angles and a Boolean.
Okay.
And then, what's it? 316 or whatever, 216 times per second. It will query from our controller what angles it's in, and it'll try and put the robot in those angles.
Okay.
And then it will, I haven't finished writing this yet, but it will, when I'm done, it'll write that data to a serial port on my computer.
Okay.
That'll just say, I'm in this position.
Mm.
And then then I can record just a series of positions that the robot is in. I'm going to completely ignore that the action space exists because it's a robot arm. Everything's interpolation.
Yeah.
So you can just, in order to get from state to state, you can do that. It can theoretically execute anything within this space, ignoring the fact that it would self-intersect a lot and probably break more than it currently is. But so once I have this data set of a whole bunch of trajectories, then I can what?
Add noise to it.
Yeah, I can take that data set of trajectories, that distribution of trajectories, and I can ruin it by adding noise to it. And I don't even really need to ruin it by adding noise. The way that is actually trained is it doesn't actually do the first step.
Okay.
It just assumes that the first step has been done.
Mm-hmm.
It's silly. It's
Okay.
very, very silly. But the way the math works is that the first step is theoretically important, but practically you can assume that it's been done. But yeah.
Are you saying you can start with
Actually,
good data?
No, you can't skip that step. Sorry, I lied. Because you do have to train the neural network. My bad. I'm mixing up the training and inference steps.
Oh.
In training, you have to ruin the data in order to train the neural network on basically the reverse of this.
Mm-hmm. Mm-hmm.
Given the error at this state, predict or given the error at this state and these states,
what kernel?
We'll learn that basically. Well, how far off is the neural network from that?
Mm-hmm.
And you can just use gradients or whatever learning you want to use for that. Actually, it's this one.
So at inference, you can just give it like that clean trajectory.
So at inference, you don't even need a clean trajectory. At inference, it has all of this data already.
Mm-hmm.
And so all you have to do is sample from this 0 to 1 and Gaussian. So it's in multiple dimensions, but this 0 to 1 Gaussian, and then that random noise will be filtered through. So there's kind of this picture where the gradient on the picture represents time effectively. So this one's already diffused quite a bit because you can tell that the later in time is closer to the end and the earlier in time is closer to the beginning. I should use my mouse in order to show people. Later in time is actually close here, and then earlier in time is actually close here. So it's actually done quite a bit of diffusing. But when you're looking at actual paths that it's working with, it'll be completely random, different colored dots everywhere. And then at each step, each of those dots will slowly shift around, or sometimes not so slowly, in order to become another different random set of dots. And then over the whole diffusing step, it'll get slowly and slowly less random until we get our nice clean trajectory. And this is really easy on a robotic arm because you can just you can just interpolate between points. It's a little harder on like a robot car because there is no guarantee that taking action A at state B will give you the next action, will give you the next state in our predicted trajectory. So that's part of what I'm actually researching right now is how do I prove that this process will be valid. Another thing is like it's impossible to prove any properties, not impossible, but it with just this algorithm, it's very difficult to prove that any properties are exhibited by our trajectory, such as non-intercepting. So this trajectory could just have the robot pass through itself. This robot is kind of hard to do that. There are a few cases when it can break itself, and it did that twice earlier today. But we're not going to talk about that. It's more important when you actually have an environment that you're in and you need to not break the Amazon warehouse that the robot arm is sorting packages in, you know, that kind of thing. I hear Amazon gets mad when you do that. So that becomes quite annoying because we have this completely random noise that we're dealing with. So one could try and consider that there's some subset of the random noise that maps to valid trajectories. But how do you find that, and how connected is it? Is it sparse within the noise anyway? But it's very interesting the way that this process maps just a completely random distribution to actually useful data. And it's quite neat. Hopefully you leave this with a little bit better understanding of what diffusion in robotics really does. You can see that it's not just a force for evil in the world, with stable diffusion stealing people's art and whatnot. That's not a problem with the algorithm itself, it's just a problem with how people are using it. But this is a way of using it for hopefully good. And yeah, those of you who are watching this later, come hit me up, because this will probably be a better functioning robot and I can record some trajectories.
Yeah.
It'll be a Rutgers day. Do you have any other comments, questions, notes?
So when you collect data with this, I was just curious what these model how big this model would be. Like just for this arm, I mean.
Yeah. So that's part of the question I want to ask with my experiments of basically what is the minimum size data set that I can make function. But the model itself isn't that big for a robot of this size. Like I've only got 5 parameters to it and one of them is Boolean. So the actual neural network itself is just a sequence of these layers here, which somebody probably knows better than me. But it takes in what diffusion time it is, what's my 3 points. I think it actually, it's not what diffusion time it is it? No, it is what diffusion time it is. I lied. Sorry. It takes in what diffusion time it is, as evidenced by the T in our error data here. It takes in what diffusion time it is. It takes in what our local region is. It convolutes that down, and it produces the the error from that. And so it has a few downsampling layers that'll take high dimensional trajectory data, and then turn that into lower and lower dimensional data. And then it'll turn it into the higher dimensional error, because we have an error term that is going to have 4 plus Boolean error. Error for the gripper is pretty easy, I'm sure. So it's not that big for for something that actually works with images, or a higher dimension robot, or a very one of the things I want to do with this is see how it works with complicated robots, like like the Tensai robot we have in Costas' lab. But for like a really high dimensional robot, like 2 arms even, or a continuum robot or something like that, then the dimensionality will be higher. For an image, it's going to be scales of magnitude higher, because there's just more data that could be there. And then you can, of course, give it toy examples of just points in a line on them and to solve a maze, that kind of thing. But yeah, it's not that big. I think this is like, I mean, everybody knows that this is pretty promising as far as things go. Similar styles of planning, that being imitation learning stuff. We know that Waymo, is it Waymo? Yeah, Waymo uses imitation learning. We don't know fully what kind of imitation learning they use, but we know that they do. We have access to their data sets. So this kind of planning is going to be important. Generally, in order to make it safe, they're building on top of it safety layers. I'm currently working on making the actual algorithm safe, but to each their own. Safety layers are important anyway.
So, what are the other like data-driven planning algorithms that I use?
So there are tons and tons of different data-driven planning algorithms for like, and there are paradigms within each of them. There's the model-based planning, in which you have your data set of transitions like this, and you're just using that to determine what is my dynamics. How does the action affect the state? That's it. I don't really care what you're doing in your trajectories, because you're a human and humans aren't good at things. I find that particularly compelling because I'm a human and I'm bad at things. But there's also stuff like factor graphs, which learn how wrong is your robot. And that's a different kind of planning algorithm, but it's still data driven and still kind of planning. And then there's of course the other versions of even imitation learning. So whatever you're doing with robot data, there's a planning algorithm for you. Like, and there are different ones that are good at different things, and etc. Yeah. One cool thing about this particular algorithm is you can do it somewhat effectively without simulations. So you can just do reel to reel. You don't have to deal with any sim stuff. Simulations are still useful for generating trajectory data, but theoretically, and this is what I plan to do, I could just take this robot around and have people do little tasks with it and then record their data and turn that into a data set. And then I have real data. And then I'll make real data from it and execute and see what happens. that'll be very labor intensive, but I can do it. And I will. Stop me. So yeah,
Does collecting this kind of data need an IRB?
but need a what? IRB? I don't know. Once I have this working, I plan on talking to people, especially since I want to get little kids involved. I want to make a data set that is just, children, because I find that particularly interesting. But I'm also very hesitant to get to do that because of
Yeah. That's really cool.
yeah. Well, that's
And
what,
even the stuff with the guaranteeing things with how the algorithm works in terms of like what noise it's learning.
the guaranteeing bit is particularly wild. There's an algorithm, or there's a paper that is on safe diffusion, basically from like 2024. That's this year, 2023. I know what year it is. Which it proves that there is a point or it learns the point in your diffusion step in which the constraints that you do that. So like say that you're going to do a simple non-intersection constraint. So it learns the point in diffusion when we're adding noise where that constraint is violated, and it proves that, or it constrains it so that every state afterwards has to violate that constraint. And then the proof is that when we learn from this data, then with near probability 1, not perfect probability, but because we're still sampling, but with very high probability, when we are doing our inference step, there will be a point in which everything after that in the denoising bit is going to satisfy our constraint, and everything before that is going to violate it. And that's so cool.
Yeah, how did they do that? It's a bunch of math.
Yeah, so basically they turn the diffusion step here, that instead of it being known, they make it its own controlled Markov process.
Okay.
So the amount of noise that I add and the amount by which I shift the mean is going to be controlled by the algorithm.
Cool stuff.
It's really cool. So that's where I was very inspired by that paper, and that's why I've been looking at diffusion more. So I feel like that gives an inroad to making diffusion a bit more scrutable, because it is quite inscrutable. That's all I have. It's 8:30. Technically, I have 30 more minutes, but I'm tired. I have to take a break.
Thanks, Noah.
Of course. I'm mad that nobody showed up.
I know. I'm sorry.
I'm gonna have to give some of my students a stern talking to. That's a joke. I can't force them to come. They have some papers and stuff to work on.